All right, nerds. Today we are going to begin actually graphing sine, cosine, and all the other functions, but we're going to focus primarily on sine and cosine because they really do help us do a lot of things. Now, I never graph trigonometry by plotting points using like tables of data, ever. I'll show you how I do it as we go along, but for now, we're just going to talk about some vocabulary, and we will do the first example by, plotting data, things like that, okay? So the sine and cosine functions relate real number values to the x and y coordinates of a point on the unit circle. Remember, sine of theta is y over r. But in the unit circle, r equals 1, so sine of theta is your y value. In any circle, cosine of theta is x over r, but in the unit circle, r is 1, so cosine of theta would get you your x value. So I guess the question is, what would this look like if we created a graph that relates the angle to a function value? And we will start with sine. So the sine function matches the measure of an angle in standard position with the y coordinate, because remember, y over r and r is 1. This point is where the terminal side of an angle intersects the unit circle. We already know that. A sine curve, also known as a sine wave, is a graph of the sine function. And, sine of theta is just your y over r. Again, r is 1, so it's just your y value. Now, unfortunately, the video won't be able to pick up what I'm about to show you on YouTube. So I'm going to pause the video so you can get a moving demonstration of what the sine function actually plots. There, YouTube video is passed. So let's go ahead and get into it. Because a full circle is 2 pi radians, the period of the sine wave is 2 pi. It takes it a full 2 pi, full circle, before it repeats itself. Okay? So the one and only time that I'm going to fill out a table for this function, and the only reason why I'm doing it is because we need to be able to answer these questions. I'm going to be real with you. I don't have the unit circle memorized. I've said this to you I don't know how many times. I am only being able to write these values because I'm seeing the sine wave in my head and I'm drawing the triangles in my head. And I've been doing that for a very long time. If you asked me, like, fast, quick, what's sine of 7 pi over 6? I'd be like, and I'd be drawing the triangle in my head if I had no paper to see what the y over r would look like. Okay? So the one and only time I'm actually going to fill out table data. Sine of 0 is 0, because when you're on the x-axis, there is no y value, so you get 0 over r, which is 0. Pi over 6 is a 30-degree angle. Across from a 30-degree angle is a 1, so this is going to give me a 1 over 2 in my 30, 60, 90. This is the 60-degree angle, so it's the other fraction that's possible in the 30, 60, 90, root 3 over 2. At pi over 2, that's 90 degrees. We're on the y-axis. And since it's the unit circle, the radius of the circle is 1. That means my coordinate is at 0, 1. I have 1 over 1, which is 1. And now we're into quadrant 2. So from here to here is quadrant 2, where the y values are still positive, but now I'm back down to a 60-degree angle, back down to a 30-degree angle, and pi radians is 180 degrees. That puts me back on the x-axis where y values are 0. So y over r gives me 0 over r. Now I'm into quadrant 3 where my y values are negative. I have a 30-degree angle, so it's going to be another 1/2, but my y values are negative, so it's negative 1/2. A 60-degree angle in quadrant 3, so negative root 3 over 2. I'm on the y-axis again, but now I'm at 270 degrees, 3 pi over 2. That's the negative y-axis. The radius is always positive, but the y value would have been negative 1 there. Back at a 60-degree angle, I'm in quadrant 4, so negative root 3 over 2. A 30-degree angle, -1/2. And back on the x-axis, because 0 and 2 pi are coterminal, there it is. So just by looking at these things, what x interval shows my y values increasing? So beginning at 0, I am increasing, but when do I stop increasing? At pi over 2. So from 0 to pi over 2, we are increasing. Remember, College Board wants us using brackets at zones where increasing and decreasing change. Okay? But starting at pi over 2, my outputs begin to decrease. So now I'm decreasing. I know I'm going to begin decreasing at pi over 2. But looking at your outputs, when do they stop decreasing? This y value is the last one. So that's going to happen at 3 pi over 2. Because after x equals 3 pi over 2, these values approach 0 again from -1, which means they're increasing once again. Like that. Now the question didn't ask about concavity, but we could have done it. We could have. I'm going to be real with you though. I feel like the concavity is harder to talk about by looking at the values. It's much easier to talk about when looking at the picture. So on the other side of these notes, when we actually have a picture, we'll talk about the concavity. Okay? Maximums and minimums. Every sine wave has an infinite number of maximums. It has an infinite number of minimums. In the first 2 pi, though, there's a single maximum, there's a single minimum. The maximum y value is 1. And it happens at pi over 2. And the minimum value is -1, happening at 3 pi over 2. Of course, those points can be manipulated through transformations, but this is just of the parent y equals sine of x. Okay? So obviously, like I said, things can be manipulated through transformations. But I never graph my trigonometry using tables of data. Because I don't have the unit circle memorized, that slows me down. Instead, I know what the parent functions look like, and I know how transformations affect all functions. And I've already talked about this earlier in the unit, but I told you that every sine or cosine wave can be broken into 4 pieces, right? That's because there are 4 quadrants. You'll never have to use this kind of terminology, but those 4 quadrants are bordered by, outlined by 5 key points. And these key points are going to be places where our graph has maximums, minimums, or places where it intersects its own midline. When you're looking at the parent sine wave, the midline is the x-axis. This can be shifted up and down, obviously, through transformations. But the 5 key points, so to speak, are midline, max, midline, min, midline. There are 5 points there. And those 5 points separate our object into 4 things, 4 quadrants. So as you can see, there are 4 zones if you're reading between the lines. 1, 2, 3, 4. And those 4 zones represent the 4 quadrants. Quadrant 1, quadrant 2, quadrant 3, quadrant 4. Other things that we've talked about are amplitude and period length. The amplitude is how far up and how far down a graph can go from its midline. Because it's how far up and how far down, the amplitude is always going to be a positive number. So we always do absolute value of whatever number sits in the front. So from here to here is your amplitude. And from here to here is also the amplitude. Oh, my goodness. That was way too large. It should have stopped. It was only supposed to go to the maximum. Sorry. And it was only supposed to go to the minimum. Sorry. But anyway, I just wanted you to see. I'm just reminding you. And the period length is how long it takes for the thing to reset. So from 0 to 2 pi. So our period length is 2 pi. Jack, question or just stretching? Just stretching. Okay. Now that we have this parent function, let's talk about how I graph sine. First thing I do is I determine, is it a positive sine wave or a negative sine wave? This is the parent function. It has a positive number in front of it, so I would label this as a positive sine wave. I know that the positive sine wave begins at its midline and goes up first. So negative sine wave would obviously be upside down. Then what I do is I determine how long the period is. I cut that period in half. I cut my halves in half. And then I go, what's my maximum, what's my minimum, and I connect my dots. Essentially, I plot the 5 key points without ever evaluating any trigonometry. Okay? And you'll see what that looks like here in a couple minutes. But before I move on, let's talk about concavity. When is this wave concave up? From pi to 2 pi, good. Remember, concavity does not use brackets. And it is concave down on the other half of its period. So 0 to pi. And just to remind you what concavity means. If you say concave up, what you're saying is the second differences are positive. That's the same thing as saying that the first differences are increasing. So if first differences are increasing, that means second differences are positive. That means concave up. Concave down means second differences are negative, which means first differences are decreasing. Just putting all those words out there to make sure that we're reviewing our unit 1 and 2 material. Better not.
Not trying.
Well, you got to figure it out. All right. Boop. So what if it's just a generic sine wave that's got some kind of transformation multiplier on the outside and transformation multiplier on the inside? Well, the domain of a sine wave is unaffected by any type of transformation, because you can find the sine of anything, because y over r will never be undefined. The radius is always a positive number. That means our domain, no matter what, is all real numbers. Oh, I did need to point this out. You see how it says x is in radians? You never try to graph in degrees, ever. Never graph in degrees, ever. Dead giveaway on your graphing calculator that your calculator's in degree mode, that when you graph trig, it looks like a horizontal line. If it looks like a horizontal line, your calculator's in degree mode. That or you forgot to type the variable x. Okay? And it only looks like a horizontal line. It's not actually horizontal. It's just that if it's in degrees, the period is 360. So you have to go from 0 to 360. So when you're looking at from 0 to 10, it's going to look relatively flat. Okay? So always graph in radians. Okay, the range. The range is determined by the amplitude. The parent range is from -1 to +1. But if I put a 2 on the front, it would go from -2 to +2. If I put a -5 on the front, it would go from -5 to +5. So if I put an A on the front, what is the general range? -A to +A, yep. And we will have to use brackets because our y values will actually be attained. -A to +A, whatever that number is. And it doesn't matter if that number is positive or negative, that's still going to be a truth. The amplitude is, well, it's supposed to be 1. The only way that changes is if you have a vertical dilation. Oh, look, a vertical dilation. But your amplitude is always positive. So it's the absolute value of A because A could have been negative. But if it was negative, that just would have flipped the graph upside down. That doesn't change what the amplitude is. You put a -6 on the front of this, the range is from -6 to +6. That makes the amplitude 6. That means I can go 6 away up or down from my midline. The period is supposed to be 2 pi. This is a horizontal dilation. Horizontal, inside, opposite. So it looks like you're multiplying your x values by b. What are you actually doing to your x values? Dividing them by b. So since the period is supposed to be 2 pi, our period can be calculated by saying what it should have been divided by b. Because it's just a horizontal dilation, which is always going to have the reciprocal effect of what it looks like. You put a 2 in front of that x, you cut the domain, or not the domain, you cut the period in half. You put a 1/2 in front of that x, oh, you doubled the period length. Okay. And these 5 key points, I'm not even going to bother writing out the formulas that I'm intended to write out, because I would never have that memorized. Instead, what I would do is, I'd figure out what my period length is, I'd cut that in half, I'd cut the halves in half, I would figure out if I was dealing with a positive or a negative version, and then I'd look at my amplitude. And I'd just plot. Let me show you what I mean. I'm not going to use this table at all. I would never do that. Instead, what I would do is I would say, what am I dealing with? Positive or negative sine? Ooh, that number's positive. So this is a positive sine wave. A positive sine wave will always go midline up. Like that. I would then determine where my midline is. Oh, well, since there's no vertical shifting, I know my midline is at the x-axis. Like that. Now, I would figure out what my period length is. Period is 2 pi over b. The number that sits in front of our x is a 1. So our period length is 2 pi. Okay, here we go. Oh, and the amplitude is 2. That tells me my maximum is 2, my minimum is -2. And I would do this. I'd say, okay, a parent sine wave will begin at the midline at 0, 0. It'll end there as well. That's 2 pi. Halfway between the beginning and the end, I'm on that midline again. So I cut my 2 pi in half. Then I cut my halves in half. It gets me this pi over 2 and this 3 pi over 2. I know that between the first and second midline hit, I'm at a maximum. Maximum of 2. I know between the second and third midline encounter, I'm at a minimum. So -2. And then I would connect my dots. So I've graphed a sine wave without evaluating any trigonometry. It's just easier than trying to evaluate trig. Know the sine wave, what it looks like, and know how to do transformations. That's it. That's what's great about transformations. I think I've said that, I don't know, at least 300,000 times this year. They affect all functions the same way. So as long as you know what the parent function looks like, and you have a knowledge of transformations, you can graph anything. You want to ask me any questions about this wave? Yes, sir.
If you were to use trigonometry, how would you do it? If there is a transformation?
So what you'd have to do is you'd have to say, well, what is sine of pi over 2? And then you'd have to multiply that value by 2. Which, that one in itself is not that bad. But what if there was a transformation here, here, and back here? Then that would just really suck. You know, it's just a lot of arithmetic and evaluating trigonometry, which if you're like me involves drawing a triangle. Or you could just know the parent function's shape and know how the transformations affect it, which is how I graph all of my trig. Boop. Hey, look, a table of data that I'm not going to fill out because I don't feel like drawing all the triangles. But Mr. M, how am I supposed to graph cosecant, secant, and cotangent? I will show you my way when we get to it. Okay? Because I feel like my way is better than memorizing all of this crap. Instead, let's go ahead and graph a transformed version of sine without this table. I mean, you could just pretty much pretend the table doesn't exist. We're going to graph that. That's what we're graphing, okay? I'm not even going to look at this. I don't give a crap what's in this table. None of this matters to me. Here's what I'm going to do. Identify this as a negative sine wave. That means it's upside down. So instead of saying from midline up, this one's going to go midline down. Now I'll determine the length of my period. 2 pi over b. Our b value, the number in front of x, is 2. Oh, the entire cycle will finish in pi radians. So what I would do if I was sketching this by hand is I would draw my x and my y. I'd put a pi on there. I'd cut that in half. Then I'd cut my halves in half. So if this is 1 pi over 4, this is 2 pi over 4, 3 pi over 4, 4 pi over 4. So you're counting by pi over 4s. And the amplitude is 3. Since it has not been shifted up or down, I know that my midline is still the x-axis. So I'll go up to +3 and down to -3. Because I haven't been shifted left or right, I know I'm still going to begin at the origin. I haven't been shifted up, down, or left, right, so I'm going to begin at the origin. I'm going to begin on the midline. I'm going to end on the midline. And by end, I mean one cycle. End. Halfway between the beginning and the end, there is another midline hit. And halfway between the first and second midline encounter, there will be a minimum or a maximum. Because it's upside down, it's going to be a minimum, so down to -3. Halfway between the second and third encounter, there's going to be another minimum or maximum, but because it's up, it's clearly a maximum, so +3. And if you wanted to keep going, you could say this is 5 pi over 4, and you could track it back down again to the next minimum, because it's going to follow that pattern. Heck, you could even track it over to this next maximum if you wanted to at negative pi over 4. And all that without this table, based on what the parent function should have looked like and the 3 transformations that we see. Because there are 3 of them. 2 verticals and 1 horizontal. Now we have to describe those transformations. What's the negative sign? Don't say flip, say reflect. Over which axis? Reflect over x-axis. Then there was a 3 on the front. Vertical dilation. Factor 3. Oop. And lastly, there was a multiplier on the inside. That's a horizontal dilation. So if there's a 2 on the inside, what is the factor? Yeah, it's always 1 over b, so 1/2. Look at that, gorgeous sine wave with no evaluating of trigonometry. When you say it's symmetric, what do you mean? When x is negative, does it not change? You mean sine. So sine of negative x, is that what you're asking? So sine of negative x, it's not symmetric, but sine is an odd function. So sine of negative x equals sine of x. Yes, because sine happens to be an odd function because reflecting it upside down is the same as reflecting it left-right. So it is odd. That's one of the... Cosine is even. Cosine is symmetric over the y-axis. So cosine of negative x... Oh no, I said it wrong. Cosine of negative x equals cosine of x. Sine of negative x is negative sine of x because it's odd. Yeah, so flipping this one upside down is the same as flipping it left-right, where cosine, flipping it left-right is doing nothing. Yep. So we don't say it's symmetric, we say it has odd symmetry. Yep. We'll do it again. And actually, I'm going to fill this space down here with an extra example as well. And so, yeah, we're going to graph this trig with no table. I'm going to pretend the table doesn't exist. Table can go bye-bye. What do I see? I see a positive sine wave. That means it's going to begin in its midline and go up. Speaking of midline, this has a vertical shift. That means my midline has shifted up too. There. Amplitude is 2. That means 2 up from 2, 2 down from 2. And the period length, 2 pi over b. So if I was sketching this by hand, I'd draw my x and y axis. I didn't do any horizontal shifting, so I would begin at the origin. Don't worry about it. I'm not going to actually put a point here because I know it's up here on the midline. But what I'm saying is I'd go out to 2 pi because that's the length of the period. I'd put a mark and call it 2 pi. I'd cut that in half and call it pi. Then I'd cut my halves in half. And that's how I would determine my x values. Okay, let's go. We know that our wave is going to begin on the midline, and since there was no left-right shifting, that's right here on the y-axis. By the way, left-right shifting for trigonometry is called a phase shift, if you were curious. I'm sure it'll come up in the notes somewhere. I'm just going to go ahead and say it now. There's no phase shifting, so we begin on the y-axis like we should. Okay. I know I'm going to end on the midline at the end of my period length. So at 2 pi, I'll be there again. Halfway between the beginning and the middle and the end, I'll be in the middle. I'll be on the midline again. And because it's a positive sine wave, Halfway between the first and second encounter, I'll be at my maximum. That's up 2 from the midline. Then halfway between the second and third encounter, I'll be at my minimum. That's down 2 from the midline. And connect your dots. And then it wants to describe the transformations. The 2 on the front. Vertical dilation factor 2. And for the shift, it is a vertical shift. And remember, College Board AP is not going to say up, down, left, and right. They're just going to use positive and negative numbers. So it's our job to say vertical shift. And since it's up, it's positive 2 units. Vertical shift, 2 units. Negative would have been down. Horizontal, positive is right, negative is left. Okay? If it was down, it would have said negative 2 units. Yep. Now I'm going to make an extra example because I want to show you how to do this without ever plotting any points. So extra example, and I'm going to do everything except for phase shift. We are going to graph without doing any trigonometry. Y equals -2 sine of 2/3 pi x plus 1. So I've got 1, 2, 3, 4 transformations here. The only thing I didn't do was phase shift it. First things first, identify your shape. Negative sign. That means from midline, instead of midline up, this one will go midline down. Speaking of midline, it's y equals +1. We could see that our amplitude is 2. It means 2 up from the midline to 3, 2 down from the midline to -1. See, I just did 1 + 2 and 1 - 2, right? So I know this y value will be at 3 and this y value will be at -1. So that shows me what kind of numbers I need to put on my y-axis. Lastly, I need to figure out what goes on my x-axis. Arguably the hardest part. So we're going to have to talk about the period length. 2 pi over b. But our b is a fraction. It's 2 pi over 3. Remember, you could take a number off the top of a fraction and put it on the side of the fraction. So that's why I was allowed to say 2/3 pi is the same as 2 pi over 3. When you divide by a fraction, keep, change, flip. So you have 2 pi over 1 times 3 over 2 pi. The 2 pi's cancel. My period length is 3. Time to sketch the graph. I have everything I need. And because there was no phase shifting, I know that my graph is going to have its quote-unquote beginning on the y-axis. But here's how I would have done this. I'd mark out the end of my period. I know it's going to go from 0 to 3 because no phase shift. I'd cut that in half and say that's at 1.5. Half of $1.50 is 75 cents. There you go. So I cut the 3 in half, and then I cut my halves in half. This is 3/4. This is a single 3/4, 2 times 3/4, 3 times 3/4, 4 times 3/4. Okay? 1/4, 2/4, 3/4, 4, well, quarters of the wave, I should say. 1/4 of the wave, 2/4 of the wave, 3/4 of the wave, 4/4 of the wave. Is everybody cool with how I came up with these x values? Because that's the most important part. Okay. Then my y equals 1 is my midline. I know I'm going to have to go up 2, and I'm going to have to go down 2. And I'm ready to sketch. It's going to begin on the y-axis because there was no phase shifting at the midline. It has to come down to its minimum, then back up to its midline, then up to its maximum, back down to its midline, and you have sketched a sine wave without doing any trig that has 4 transformations on it. And they can be that easy. Honestly, if there's no phase shifting, trigonometry is extremely easy to graph. It's the phase shifting that makes it a pain in the butt. It'll show up eventually. Do you have any questions for me, nerds? Or can we call it a shorter than normal lesson? What do you think? Short lesson? All right. Appreciate you.